So, hi everyone. My name is Octavio. I come from Mexico. I did my undergraduate and master's back in the National Autonomous University of Mexico, and now I'm making my PhD here at the NRS, Quebec City, with Pierre-Simon Ross and Patrick Mercier-Languevin. So today I'm going to present the ultramafic to intermediate volcanic rocks of the Stoughton-Roquemaure assemblage, so the geochemical features. So let's change here. So we're working on the Abitibi greenstone belt. You must know it already. It has been subdivided into 7 volcanic assemblages, mainly on chronological constraints, lithology, and some geochemistry. It's located in the Superior Province, North Canada. And one of the interesting here is how BMS deposit has been distributed in the volcanic assemblages. We can observe how Blake River, Kit Monroe, and the Laurel contain the most of the BMS tonnage in the Abitibi greenstone belt. So we've been working making the geochemical features for each volcanic assemblages. We already work on the Blake River. Some of you have seen this, and now we're going to work in the Stoughton-Roquemaure, as the title says. We want to compare what are the chemical differences there between one assemblage that is really endowed and the other one that is really poor. And here we can observe also what are the surface area between the Stoughton-Roquemaure, 33.5%, and the Blake River represents 10%. So the problems here for this PhD project is that the geochemical evolution for each volcanic assemblage is not what known in detail. So if we are trying to observe what are the differences in terms of geochemistry and then trying to relate there with the BMS fertility is complicated. So that's one of the aims for this project, try to characterize the petrogenesis for the subalkaline volcanic rocks in the assemblages. And for that, we want to pay attention that these volcanic rocks that goes from ultramafic to felsic. So for that, we want to assemblage a large lithogeochemical of the available database. On the subalkaline volcanic rocks, we want to screen for samples for data completeness and also for quality in the data. We are looking for the whole set of major elements, trace elements, and loss in ignition, for example. When we have that for each volcanic assemblage, we want to classify the rocks. We want to create geochemical groups in terms of the composition, magmatic affinity. And with this, document the petrology and define the petrogenetic evolution in the Abitibi. We want to answer from the point of view of the geochemistry, what are assemblages, why they are more fertile and more poor endowed BMS, and if there are some geochemical signatures that could be related to BMS deposits. So we are working on the Stoughton-Roquemaure now for this analysis. This is the number of the data that we collect. And the Stoughton-Roquemaure is this pale green color here. It's well distributed in the whole Abitibi. In total, we have 747 samples that goes from ultramafic to intermediate compositions. We are excluding felsic rocks. So let's start with the comatites. We isolate the comatites on the Jensen cation plot. We subdivide them between ultramafic comatites and comatitic basalts. You can see the numbers, how many samples we have from each group. And here we have the rest of the mafic and intermediate rocks. In terms of comatites, we are not screening for alteration yet. So when we go to mafic to intermediate compositions, we have a complete data set that it's made from 712 samples. We subdivide between mafic and intermediate in this Pierce 96 plot. We have the number of mafic and intermediate samples. Then we create a subset to analyze major elements. For that, we use the alteration box plot. to have the least altered samples, and at the end we have 600 samples. So when we observe major elements, we can observe here Harker diagrams. When we are using, on the x-axis, we are using as a monitor of fractionation, we're using magnesium, and compare it with several elements. In this case are titanium, iron, alumina, and silica. So we are, and the groups that we are showing here is based on the trace element, but we are going to address this a little bit later, but we can observe here two major clusters between these purple and these blue ones, and the content of magnesium in the comatites. So the interpretation for that, first we have having the comatites. That could be, our interpretation is that could be related with the Enmore group, which is this purple group, and this content in the comatites could be related to olivine fractionation and or the degree of partial melting. And then when we arrive to more mafic compositions, more or less about 10% of magnesium, then we we have this distribution of this on the mafic magmas potentially could be related to water contents on the magma. So where we're observing here, and these lines over here represent more anhydric composition, and this part we are observing more water content on the magma. So typically, if you are having more anhydrous composition, then your magma is going to be rich on iron. It's going to be enriched in iron and titanium. Then you reach a point where you saturate these elements, and these go into oxides, and then you deplete your magma in these elements. And if you observe that, for example, here in alumina, and here we have the more anhydrous compositions here in the bottom, and the more rich water content on the top. So if you're having less water on the magma, then you start forming plagioclasts earlier. So that depletes the magma in alumina. And then if you're having more water, then it tends to be forming a little bit later. So that enrich a little bit on alumina, the magma. So, however, we are lacking here the rest of the modeling is really good to explain the distribution here on the rest of the samples. We are losing something here. So this could be, that's an hypothesis, could be related to a mixing or a contamination with, for example, a TTG. We put here the average of the Southeast North Superior average, TTG. So, yeah, so let's continue. So this is the Pierce 2008 plot. Here's where we are making our separation between the geochemical groups. And just to explain a little bit, the Pierce 2008, we're having here the mantle reservoir. The previous talk, you saw it already. We're having the depleted magmas here. We have the rich magmas, more enriched magmas over here from the YB reservoir. And for example, if we are having a component here, for example, if we are observing the volcanic arc array, we can introduce thorium on the magma, and then you will create a volcanic array that typically plots parallel to the mantle array. You can observe here for an example for these white squares for the Mariana arc. But another interaction that we can observe here is if we observe assimilation and fractional crystallization processes, when you are assimilating another material there that could be represented by AFC curves here. So if you have a depleted magma and you are having an assimilant over here, you can create this, let's say, curves over there that could be are explained by the AFC. So we already did that for the Blake River group. We established potentially 3 mantle sources. We create our AFC curves here, and we establish from there levels of contamination, 5%, 0 to 5, 5 to 20, and beyond 20%. We already did that for the Blake River group, and we create this. And we did the same approach for the Stoughton-Roquemaure, as you can observe here in the geochemical grouping. So we create the similar groups here just to make a comparison with the Stoughton-Roquemaure. We have two main sources. One that is more depleted, we call it N-morb. We have the E-morb that is more enriched. So using these only 2-3 elements, we compare it in another discriminant tectonic plots where you use more elements here, for example. And we observe that we are having good clustering, tight clusters there to observe. They typically have, for example, in the morb field, in the agro wall, and these blue guys that are being more affected by the assimilant or for contamination. These guys are being shifted into these island art basalts, and we are having here the TTG average plotted here just to observe. In the case of comediites, we put it here. We split it into uncontaminated and contaminated here. So the uncontaminated guys are close to the mantle right here, and the contaminated are here in the top. So these guys from the INMOR, they typically have a tolytic to transitional affinity, something similar for the EMOR groups here. They plot in mostly in the transitional, but if we observe the most contaminated, these guys tend to plot between the transitional and mostly in the calcaline field. And the similar happens to the comatites that are being contaminated. So just to validate of groups, we use the extended trace elements. And in here we put the two main sources, the N-morb and the E-morb group. And in this plot, you can observe between the Mayfi composition and the more intermediate compositions here. So if we are only having fractionation, the content in the trace elements only increase, but they typically have a parallel signature of the more Mayfi composition, and they only change in titanium because titanium is being more fractionated in the more intermediate compositions. But we observe for this N-morb group very flat line. Low concentrations in thorium and niobium, and that means that they are coming from a more depleted reservoir. When we observe if we are having a little bit of contamination, 5 to 20%, we observe here more content in thorium in general, a little bit on the light red earth, and the heavy red earth mostly stay the same. So for the EMOR source, these guys are less abundant. We are going to see the percentage now in the following slides, but these guys are less abundant, and they typically have an enrichment in the light rare earth, and they form a little bit of a steep in the heavy rare earth. They also are having zirconium and hafnium anomalies, positive anomalies. So if we observe here the EMOR contaminated, we can observe how the introduction of thorium a little bit more in the light rare earth, but they already have light rare earth from the let's say original source. So let's go to the next one. When we are having more than 20% of contamination, we are plotting here both mafic and andesites. They are having similar profiles, really rich in thorium, rare earth, positive anomalies for the more intermediate composition in zirconium and hafnium. It's not present in more mafic compositions. And for the case of comatites, we are seeing that for samples that are uncontaminated, they are having low concentrations in trace elements, but with a very flat line. You know, that means high degrees of partial melting for the source. But for comatites having more contamination or having this contamination, this trace element could change. And here in the bottom, we could see the potential assimilants that could be affecting on rocks. This is the TTG from the southeast, from Mole. This is more local, and here we are having the Archean crust average. So let's observe how it's our distribution of these geochemical groups in the Stoughton-Roquemaure. So in here we are observing this wide range of distribution in terms of in the Stoughton-Roquemaure, for example, in the center here we see a dominance of the NMOR group with some contamination going on there, both happening in the Chibougamau area, more contamination, but also NMOR sources going on there. And here in the top we see this dominance of more andesitic compositions and also more contamination going on there. Just to make the comparison with the Blake River group between these two assemblages, and this is only comparing the mafic to ultramafic to intermediate composition. We're excluding felsic rocks here. So in terms of comatites, we are not having those on the Blake River group, but the Stoughton-Roquemaure forms more or less between 3 and 4%. In terms of basalts, we're having 65% in the Stoughton-Roquemaure and the 74% in the Blake River. Basaltic and andesites, they are having the similar numbers, 26%. Here of the percentage of altered samples, we are having more altered samples in the Blake River rather than the Stoughton-Roquemaure. And in terms of sources, here we merge the less contaminated and the mildly contaminated samples in these groups just to observe what are the sources, and beyond 20% of contamination, we call it unclear or contaminated. Anyway, we are having 53% for the Stoughton-Roquemaure, Blake River 47%. For the EMORP, we are having similar numbers, 9 to 11% here, and the unclear we're having a little bit more in the Blake River, 42%, but kind of similar in the Stoughton-Roquemaure. So, observing the degree of contamination, but dividing between mafic and intermediate compositions. So we merge here the less contaminated groups, and then the mildly contaminated, we merge these two guys, and then the more contaminated. So for 0 to 5%, we are having more samples, more percentage of samples in the Stoughton-Roquemaure, rather than the 21 from the Blake River. Mildly contaminated, 18% for mafic in the Stoughton-Roquemaure, 5 for the intermediate, a little bit more in the Blake River. We are having 29 compared to the 6% in the intermediate compositions, and more than 20%, that's where we are having a big difference. For the mafic composition in the Stoughton-Roquemaure, we are almost not having mafic composition, but we are having more intermediate, that is like 28%. And for the Blake River group, mafic compositions having more degree of contamination are having 26%, and 16 from the intermediate. So one of the characteristics that we can observe here for the Stoughton-Roquemaure is we put here an arbitrary line just to subdivide the north and the south. And the south and central parts could be a dominance for this NMOR that I already mentioned. We have comatites, a lot of comatites going on here, and even more here. And for the northern Abitibi of the Abitibi, we can observe more contamination happening on the Stoughton-Roquemaure. So, in general, the comparison with the Blake River, we have fewer altered rocks, we have a significant presence of comatites. We also have, in general, basalts have the similar source, they're mostly NMORP. Basalts tend to have low degrees of contamination in the Stoughton-Roquemaure, and the andesites could be typically contaminated. Here we create this plot just to illustrate this thing. The andesites are more contaminated. Here we could see fractionation on the X and contamination using Toyon-Terbium ratio. So the more mafic compositions tend to be around here. We can observe this dominance of basalts being from the NMOR group, and just a little bit of contaminated basalts plotting in the basalt field, or where the ratio of the basalts should be. and for more andesitic composition, we are seeing not too much of fractionation from these rocks, but a lot of contamination going on in the more andesitic compositions. So another attributes that we could compare between the Blake River and the Stoughton-Roquemaure, we can say that the Stoughton-Roquemaure is more widespread in the Abitibi greenstone belt. It was in place much more quickly. For the Stoughton-Roquemaure, it was 3 million years old, and for the Blake River, it was 9 million years old. So potentially, Stoughton-Roquemaure has more bigger magma volume. Here we have the comparison between the areas that we already saw. And the Stoughton-Roquemaure could be a possible oceanic plateau in origin, and that could come from a mantle plume. So, and then the Stoughton-Roquemaure, we only have one small BMS deposit. So our future work is continue to work with the classification and petrology in the Stoughton-Roquemaure. We want to refine the construction on our geochemical groups. We want to integrate the felsic groups and do the same for the Blake River and compare the whole suite of rocks. And we are going to try to refine or try to observe if there are some subdivision in between the north and part, and the north and the south and the Stoughton-Roquemaure. We don't know yet. That's the preliminary results that we're having here. And we want to continue looking into other assemblages. So, yeah. And that's it. Thank you. That's a big question. When we're working on the Blake River, we will mention that it's contamination, but now potentially could be we want to call it as unclear, because they are having high thorium-ytterbium ratios, and when you observe their signatures, are very different from the guys that are having a depleted mantle source. So, but yeah, at the end. Our initial thoughts is it's happening contamination there.
Contamination as in crustal or?
Yeah, crustal contamination. Yeah, from a TTG and all for a previous crust.
In previous talks, the Abitibi has been compared with alpha systems.
Mm-hmm.
You discriminate comatians just because they appear in a classification diagram.
Yeah.
And they be also pictures and pictoacids, which are also common in alpha systems. Did you check for textural evidence of comatians, or if they are just coming out of the classification diagram?
So we only screen out with according to the chemistry, yeah, but we have not checked these things.